All right, problem 15, number theory. So we have this 5-digit number divisible by or integers between 1 and 11. Find the sum of these digits. Okay, so let me first list all numbers between 1 and 11. Okay. Now, actually, we don't need to consider all these numbers because some covers other numbers. So, for example, if the number is divisible by 9, that means we don't need to consider 3 because it's divisible by 3 automatically. And also, if the number is divisible by 8, we don't need to consider 2, 4 because that's automatically true. And now, once we have the number divisible by 8 and 9, we don't need to consider 6 because if it's divisible by 8 and 9, it's divisible by 6 automatically. And of course, 1 can be just ignored because any number is divisible by 1. And now for 5, we can simply choose 5. If a number is divisible by 5 and 8, we don't need to consider 10 because it's automatically divisible by 10. So finally, we only need to consider the number divisible by 5, 7, 8, 9, and 11. Okay. So let me call this number n, A, B, C, D, E. So we have n is divisible by 5, 7, 8, 9, 11. So, okay, 5, let me write. N divisible by 7, n divisible by 8, n divisible by 9, n divisible by 11. Now we just consider the least common divisor, least common multiple of these numbers 5, 7, 8, 9, 11. The least common multiple of this 5 number equals 27720. From above, we see that such n only needs to satisfy the requirement that 27720 is a divisor of n. Any number satisfy this will satisfy the requirement in the problem. Now let's see that n is a 5-digit number. There are several choices. And could be just 27720 or n equals twice 27720, which is 55440, or n is 3 times 27720, which is 83160. So there are 3 choices for the number n. Okay? But in the question, we are looking for the sum of these digits. But for these 3 cases, they have the same sum of digits. That's just 18, okay? 18. It's always 18, so the answer is 18. All right, problem 16. Coordinate geometry. We have 2 lines intersect at a point 9, 12. So we partially know the formula of the lines. From this intersection point, we can solve these lines completely. So for example, for the first line, it passes through 9, 12. That means we can just plug in 9, 12 to the equation. So y equals 12. That corresponds to 2 times x. X is 9, and plus 8. And that means a equals minus 6. Similarly, for the second line, y equals 3x plus b. So 12 equals 3x plus b. That means b equals minus 15. So the first line is just y equals 2x minus 6. The second line is y equals 3x minus 15. Now we know these equations and we can draw these lines in the coordinate system. This is the x coordinate, this is the y coordinate, this is the origin O. Now for the first line, y equals 2x minus 6. So the y-intercept is minus 6. And the x-intercept corresponds to y equals 0, which is when x equal to 3. So there's 3 here. So this corresponds to the first line. Now for the second line, we have 3x minus 15. So the y-intercept is negative 15. And the x-intercept is when y equals 0. So that corresponds to x equals 5. So x equals 5 here. So this is the second line. So we have these 4 intercepts. We can denote them by A, B, C, D. So let me call this A, B, C, D. So this is a quadrilateral A, B, C, D. We want to find the area, okay? Find the area of this quadrilateral. So we see that this quadrilateral is the difference of 2 right triangles. So this is a quadrilateral. Area of ABCD equals area of the big triangle OCD minus the area of a smaller triangle OAB. Okay, and then the area of a big triangle OCD is 1/2 times 5 times 15, and the area of smaller right triangle is 1/2 times 3 times 6, and then we get a solution. This corresponds to 37.5 minus 9, which is 28.5. So the answer of the quadrilateral is 28.5. All right, problem 17. We have a boat traveling upstream in the river. Under Bridge A, a plastic suitcase was dropped, and 20 minutes later, the owner realized this and come back to chase for the suitcase. It was caught 2 kilometers downstream from Bridge A. We want to find the speed of the river. Okay, now we have 2 speeds. One is the speed of the boat. One is the speed of the river, the water. So let me use notation to denote these 2 speeds. Speed of the boat. Let me see, speed of the boat in still water, okay? Let me call the VB, so V boat. And the speed of the water. Let me call the V water, okay? So let me draw a picture. Suppose this is the Bridge A. At Bridge A, a suitcase was dropped. Let me call this time t equals 0, okay? And this suitcase will carry downward by the water. So after 20 minutes, which is just 1/3 hour, after 1/3 hour, the location of the suitcase will be here, which is 1/3 V water, okay? And we can consider the location of the boat. The location of the boat is upstream, okay? And of course, the boat speed is larger than the water speed. We see that the boat may be here, because the boat speed and the water speed are have opposite directions. So this distance is 1/3 V boat minus V water. Okay. This is a boat here. This is a suitcase. Suitcase here, right? Now the boat start to turn around and chase the suitcase. Now let's see what's the distance between the boat and the suitcase. This distance is basically 1/3 V boat, okay? 1/3 V boat. And if the boat start to chase the suitcase, the boat speed will be the speed of the boat plus the speed of water. Okay. Let me denote this by, okay. The boat's speed is the boat's total speed is VB plus V water. That's the boat's total speed. And the suitcase speed is just the water speed. So the difference of the speeds will be just VB. And this times some time, right? Some time, maybe let me use T times some T. And of course, we see that T is just 1/3. So it implies T is 1/3. That means it takes 1/3 hour to catch up this suitcase. It's still 1/3 hour. Okay. So maybe I need to draw another picture. Okay. After another 1/3 hour, this is original 1/3 hour. After another 1/3 hour, the suitcase will be here. T equals 2/3 hour. The suitcase traveled another 1/3 VW, okay? And we see that this distance is 2 kilograms. Sorry, 2 kilometers. So 2 kilometers. And we know this corresponds to 2/3 V water. And that means V water is 2 times 3/2, which is 3 kilometers per hour. So the speed of the water is 3 kilometers per hour. Okay, this is like the method 1. This is method 1. It's like a standard, but it's a little bit complicated. Now we can actually solve the problem in a very easy way. So in problem 1, we consider all speed relative to the ground. Okay. Now we can consider all speed relative to the water. If we consider all speed relative to the water, that means we can relative to the water is still. So that means the suitcase stay with the water is still, okay, relative to water is still. But for the boat, it always have the same speed, VB, okay? So if the boat realized the suitcase was dropped after 20 minutes, and when it goes back to chase the suitcase, it takes another 20 minutes to catch this suitcase. Yeah, and of course the distance the suitcase has already traveled is 2 kilometers, right? 2 kilometers equals 2/3 times the velocity of water, and that just gives velocity of water is 3 kilometers per hour. Okay, so if we consider everything relative to the water, you can just regard water is still, relatively it's still, and the boat always travels by the same speed. Okay, after 20 minutes to realize the dropping of the case, it also takes 20 minutes to come back to the location of the suitcase. So we got a time and we got a distance, we got the velocity, which is 3 kilometers per hour. All right, problem 18. We have 10 transistors, 7 are acceptable and 3 are defective. So each time we test one of these transistors, and then after the test, the product is marked and put aside. So the inspector will keep testing until he is able to determine which 3 are defective. Now the question is, what's the probability that he needs to test 7 times? Okay. So we can view the problem as follows. So the order of testing this product is like to, each order corresponds to a permutation of these 10 products. For example, like I can just draw 10 circles. Okay. So let me just test from the left to the right. So the question is how many such, okay, what's the probability of testing 7 times? So totally we have 10. Okay, because we have three defective products and 7 accepted products. So the permutation of the permutation corresponds to 10 choose 3. Okay, the location, 3 location for the defective product, 10 choose 3, which is 120. Now the question is how many permutations allows us to test the product exactly 7 times. So there are basically 2 cases. The first case is that all 3 defective are tested in this 7 testing. Okay, let me mark this here. So we get this 7 defective product in this 7 testing, but it's because it's exactly 7 testing. That means the 7th testing must be defective. Otherwise, we just need fewer testing, right? And now we have 2 other defective products tested in the previous 6 testing. So for such permutation, we have 6 choose 2, okay? For the other 2 defective products, 6 choose 2 ways to do this. So this corresponds to 15, okay, 15. But there's another way we can also determine, because in the problem, we only need to determine which 3 are defective. There's another way to determine this. That's the following. Or this 7 tested products are acceptable, okay? Suppose all these 7 are acceptable, that means the remaining 3 products must be defective. This also tells us which is defective. So this is also the case we should consider. So that means we just have one way to arrange this, right? So totally we have 15 plus 1, which is 16. We have 16 arrangements that allows us to determine which 3 are defective. So the probability is 16 over 120, which is 2 over 15. So the answer is 2 over 15. All right, problem 19. So this problem is a number puzzle. Here we can basically work backwards. So let me denote number n as this number. We only know the last digit is, okay, this little n, okay, little n. Maybe there's some typo, it doesn't matter. Okay, n. So last digit is 7. Now we move the last digit to the first digit, and the new number is 5 times of original number n. So let me call this new number m. So we shift by 1. So the first digit becomes 7. All right. So we can basically work backwards. So we know that m equals phi n. Okay, phi n. Now what let's do is, so we just multiply n by phi. Although we don't know the other digits, but we know the last digit. We know the last digit, we will know the last digit of m, because 5 times 7 is 35. That means the last digit of m is 5, because we multiply by 5, okay? So the last digit of m is 5. That means the second last digit of n is 5. So here is 5, okay? And then we do it again. We multiply by 5. Multiply n by 5, we get the next digit in m. For example, we multiply this by 5. 5 times 7, 35. 5 times 5 is 25. 25 plus 3, 28. So the unit digit correspond to this is 8. So here we have 8. The next digit is 8. And similarly, the third last digit in n is 8. And then we do it again. So now you have a question, when do we end this process? When do we end this process? Because m and n have the same number of digits, and m is 5 times n, and the first digit of m is 7, and easily we know that the first digit of n must be 1. That's the only possible digit, okay? Such that m is 5 times n. So once we see 1 appears, we can stop. Now let's do this. So now we have 28, right? 28. Five times, okay, 5 times 7, 35, 28. Now we have 5 times 8, 40. 40 plus 2, 42. So here the next digit should be 2. And similarly, this should be 2, okay? And then we multiply by 5 again. So it's 10. 10 plus 4, 14. So the next digit here is 4. Okay? And then this is a 4. Okay? And if you multiply by 5, so we get 21. Okay, get 21. So and now we have 1 here. And now we see the 1. So we can just stop here. So this is like work backwards. And so the answer, the n is just 142857. And the question is to ask the sum of digits, okay? 1 plus 4 plus 2 plus 8 plus 5 plus 7, which is 27. The answer is just 27. All right, let's come to the last question, 20. So here we have 21 rectangle boxes, and we put natural numbers in each of these boxes. So we want to maximize the number of odd numbers. Okay, let's see that each number here is the sum of 2 numbers below, okay? So we have the following fact. For natural number, we have 2 cases, even number or odd number, right? For odd number, if we want to split odd number, it has to be odd and even. Okay, and if we split an even number, there are 2 cases, right? Odd plus odd, or even plus even. Right, in our problem, we want to maximize the number of odd numbers. So that means this is not a good choice, okay? So we'd like to use the previous 2, as many as possible. Now we see that, okay, if we write this into a rectangle, into these triangles, we have odd, and below odd number, we have odd and even. And for the second one, we have even. For the second one is even, responds to 2 odds. Okay, So let's look at these two triangles, okay? These two triangles. In each triangle, we have 3 numbers. And we see that there are 2 odd numbers and 1 even number. That means basically we have 2/3 odd numbers. Here is also 2/3 odd numbers. So let's see the boxes. Here we have totally 21 boxes. Right? So roughly speaking, 21 box times 2/3, that's 14. So we can roughly have 14 odd numbers. That's the maximum number, and that's the answer. Of course, this argument is not that rigorous. Now let me give you a rigorous argument. So we can do the following. I will divide this boxes into several groups. For example, let me draw this one. I can consider this to be a one group. And this, the second group. In each group, I put 3 rectangles. Okay. And okay, let me try to use different color to distinguish this. Groups. Now we have 6 groups, but we still have 3 boxes remained. They are, let me call this X, is Y, Z. So X, Y, Z are not included. Other than these 3 numbers, we have 6 triangles, right? 6 groups. For each triangle, we have at most 2 odd numbers. Let me write down. For each of the triangle here, there are at most 2 odd numbers. So totally we have 6 triangles. So we have 6 at most 6 times 2 odd numbers. But now we have 3 numbers remain, X, Y, Z, right? Let me write this way. Number of odd numbers is less equal to 6 times 2, okay? Each triangle contribute at most 2 odd numbers, and plus these 3. We have 3 X, Y, Z numbers remain. So this is 15. This is 15, okay? So from this argument, we have at most 15 odd numbers, but let me notice that 15 cannot be obtained. Okay. Suppose, okay, so if 15 is obtained, that means all X, Y, Z are all odd numbers. Or odd numbers. And okay, if Y, Z are all numbers, we will see that, let me denote this by A and B. That implies A, B, because A is Y plus a number, the top of the green number. So A, B have the same oddness or evenness. Okay, because Y, Z have this, Y, Z are odd numbers. A is Y plus a number here. Let me see. This is T, for example, this is T. Because A is Y plus T. B is Z plus T, right? And Y, Z are odd numbers. T, whatever it is, it doesn't change Okay, anything, because A, B will have the same oddness or evenness. If T is odd, then A, B are both even. If T is even, then A, B are both odd. So we have A, B, they have the same oddness or evenness. But we know that X equals A plus B. X equals A plus B. It has to be even. So we cannot have all X, Y, Z odd numbers. We have at most 2 odd numbers here. So the total number, okay, the maximum number of odd numbers is 14. So the maximum number is 14. And now let me show you an example that 14 can be obtained. So I'd like to move to the right a little bit and play. 14 can be obtained. Let me do this example. So the top, let me use odd. Below that, I have even and even. Okay, and below that, I have, okay, I should maximize all numbers. So below even, I have this odd. Okay, sorry, I made a mistake. This should be odd. Odd is even plus odd. So this is odd plus even. Even equals odd plus odd. Now below that, we have this is odd. This is even. This is odd. This is odd. Okay. And then below that, we have even, odd, odd, even, odd. Now for the last row, this is odd, this is odd, even. This is odd, this is odd, this is even. Okay, so in this example, we have 14 odd numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, sorry, 12, 13, 14. So 14 is the maximum number of odd numbers. Okay, and that's the solution, 14.